Numerical Computation, Chapter 2, Video 10. We will now look at Chebyshev nodes for polynomial interpolation. These nodes were designed to optimize the choice of nodes in a way that the error will be distributed equally throughout the interpolating interval. There are two different types of Chebyshev nodes. Let's look at the first one, type 1. Those are the nodes that include the endpoints. So x1 and xn will be set to be a and b, and the remaining points in the middle are chosen in a way to optimize. And we will not go through the details of the derivation. We'll just present to you what these nodes are. So if you have an interval from 0 to 1, and these are the nodes. So we put a line bar on top of it to indicate these are the Chebyshev nodes. So it's cosine I over n pi, where I runs from 0, 1 to n. So you see, if you just look at x bar I, this is not a uniform distribution. If you have a general interval, let's say from a to b, the Chebyshev nodes will be just the nodes from 0 to 1 with a linear translation onto the interval from a to b. So you get the following. Xi bar will be a half a plus b, the midpoint, times a half b minus a, that's a rescaling factor, and of the cosine, that's the same. Okay, so I runs from 0, 1 to n, the same, n plus 1 points. With this choice of nodes, one can actually show the following. That is, the term in the error estimate that's determined by the choice of your points, this product here, the maximum value of it for x on the interval from a to b, if you choose Chebyshev nodes, this exactly equal to 2 to the negative n. And what's remarkable is actually the following. So this is actually a lower bound. So this is less than or equal to the same thing of this quantity where you choose any other nodes, xk, that is not Chebyshev. So in a sense, this says the Chebyshev nodes is the optimal choice if you want to evenly distribute the error. We can now plug in this bound into the error bound and have the error bound for the Chebyshev nodes. So this is where this estimate goes in from here. That's the product term. So Chebyshev nodes will give me this error estimate. Okay, let's take the same example that we did with the uniform nodes. That is, f of x equals to sine pi x. And we want to have an error bound if we use Chebyshev nodes, n plus 1 of them. By using the formula we had, we can plug it in because we have the bound on f to the n plus 1 derivative, which is just pi to the power n plus 1. And that's the bound for the product term. So we easily get this. And we also did some simulation, and we plot the error in a similar way, where n is the number of intervals, and here the error bound is the theoretical error bound computed with this expression, and the measured error is our actual simulation where we find the error. So we see that this error bound is actually much sharper comparing these two. They are really close, and also these two are really close, and also these two. So not only is this error bound sharper, and we also see that the error is actually much smaller. You see, this is 10 to the negative 11, 10 to the negative 11. And remember, with the uniform grid, we get actually 10 to the negative 9. So there is a second type of Chebyshev nodes which does not include the endpoints a, b. So they are chosen strictly inside the interval. So the expression for these nodes is given here, so that's again the shift to the midpoint of interval AB, and that's a scaling factor, and it's this cosine function that distributes the xi's on this interval from A to B. So theoretical aspect of this type 2 Chebyshev nodes is very similar to type 1 Chebyshev nodes. It also equally distributes the errors. Now before we end the chapter, we make a few discussion. So we see for polynomial interpolation, if we allow n to grow large, in the end we have a polynomial of a very high degree, and these are actually becoming heavy to deal with. And second, and probably the worst thing, so theoretically, if you increase n, your interpolation polynomials do not converge to the function in general. And further, we observe that if you choose very small intervals, if your interpolating points are rather near each other, then the error is actually very small. So hopefully with this discussion, you agree with my conclusion, that is, instead of increase n to work with polynomials of higher degree, it might be a better idea to use piecewise polynomial interpolations, that is, use polynomials of reasonably not so high power, but we make the intervals small. Okay, so this actually leads to the topic in our next chapter, that is splines.